Let R be the region bounded by y equals square root of x, y equals 3, and x equals 0. Set up and find the volume of the solid obtained by rotating R about the y-axis using the method stated. So they give us a graph on this one, which is nice. So this is y equals the square root of x, meaning this curve right here. This is y equals 3, meaning that line up there on the top. And this x equals 0 is this line going straight up, right? It goes through the x-axis right through 0. Anyway, and then you take that and you're going to um, rotate that region. This is region R. We're going to rotate region R about the y-axis. So this, as you know, is the y-axis right here. This is the x-axis. So we're going to rotate this whole region about the y-axis, and so we get that kind of shape, right? So they gave us a little graph there to help us out. I went out to use our uh, disk washer graphing thing and got a couple graphs as well. A little more help here. Here's an overhead view of this is the x-axis, the y-axis, just straight overhead. See the different disks that we're going to fill it up with. Here's a more three-dimensional view of how it looks. Anyway, back to it. So it's going to create a volume. So when you take this region R and you rotate it about the y-axis, you're going to get this three-dimensional volume. Specifically, you're going to get this kind of shape. We're gonna fill it up with disks. Okay. And so how do we find the volume? Well, you got to take the volume of each disk. That'd probably be best if I go down here. The volume of each disk is going to be equal to pi r squared times dy. Do you see why? Because this is the circle top and the thickness is dy. So the top circle is pi r squared, right? Each of these is a circle. You can see it right here, right? Let's take this one. Each disk is a circle. Area of a circle is pi r squared. And then its thickness is dy. Why? Well, you can see it right here most easily. See how this is the y-axis and the thickness of each layer is dy to the dy direction. So there we go. Plus, they told us dy right there. So we knew it was coming. So that's the volume of each disk. Now, what's the radius of each disk? Well, the radius of each disk, let me just take this yellow one right here, this orange one or whatever. That's his radius, right? Radius of a disk is from the middle to the edge. What is that? That's the x value. That's the x value, right? To what? I'll just write x value. X value to this curve right here. Whoops, I missed a little bit. To this, I missed again for 2. To that curve right there. What's the equation of that curve right there? Well, that's y equals square root of x. So that's y equals square root of x. But we want the value from, let me just change the color here, from the center over to there. That's the radius, right? It's the radius of a disk is from the middle to the edge. That's the x value. So I got to solve this for x. So square both sides. Square removes the rooting. So x is y squared. So x is y squared. So this is going to become pi x squared dy because again, x is the radius. All right, you tracking with me? X is the radius from the middle to the edge. That's the x value. So the radius is x. But x squared, what is x? X is y squared. So now we've got it. We're going to take the integral. And where are we going to integrate from? We're going on the y-axis, right? dy. So from 0, looks like up to 3. from y equals 0 to y equals 3. And these are y values because we're integrating dy. Each of those disks, you can see over here in the 3D view, each of those disks, we're adding up each of those disks. And so that will do it. And to be sure, by the way, that it hits at 3. Oh, yeah, we can see it up here as well. So there we go. There's the answer. We set up the integral to find the volume of this three-dimensional shape made out of disks. And an integral, by the way, I know this doesn't look perfect, but it will be perfect because an integral has infinitely small disks. We're just using bigger disks to show it. And so there we go.